Assalamualaikum warahmatullahi wabarakatuh. Our group represent our SCL for MTH3202 Modern Algebra. Our group member is me, myself, NURUL binti AZNAWI, SAHIRA binti SHAMSUDIN, Aqilah Fakhira binti AYUB, NORATIKA RUSMAN, and MOHAMAD HAZRISHAM bin RAHMAN. So we proceed with the next slide. From Lagrange theorem, if G is finite group of order n and H is subgroup of G, then the order of H d by n. Theorem 1 states that let G be a finite group of order n such that n is divisible by a prime P, then G contains n element of order P and hence subgroup of order P. Theorem 2 states that let G be a finite commutative group of order n. If m is a positive integer such that m d by n, then G has a subgroup of order m. Next, for task 1, it asks us to apply theorem 1 to prove the following theorem 2. So for the solution, from theorem 1, we know that G is a finite group of order n and m d by n. So we let m equal to P1, P2, P3 until Pn, where P1, P2, P3 until Pn are prime, but not necessarily distinct. So we have m d by n is equal to P1 d by n. From theorem 1, we also know that G has a subgroup of order P1, which is H. Since G is a commutative group, thus H is normal in G and G over H exists. So the order of G over H is order of G divided by order of H equal to order of G over P1. Thus we get P2 divided by order of G over P1. Next, G over H is a finite commutative group and P2 divided by order of G over H. By theorem 1, we know that G over H has a subgroup of order P2, which is K. The subgroup K of G over H is in the form of G1 over H, where G1 is a subgroup of G containing H. Thus the order of G1 is order of G1 over H multiplied with order of H. G1 over H is K, so we get order of K multiplied with order of H. We know that K has order of P2 while H has order of P1, so the order of G1 is equal to P2 P1. Then G over G1 exists, so the order of G over G1 is order of G divided by order of G1 is equal to order of G over P2 P1. Thus we get P3 divided by order of G over P2 P1. If we continue the argument until n, so we can reach to a conclusion that after some finite number of steps at some subgroup of Gn-1 of G such that order of Gn-1 is Pn until P1, which is equal to D. So we have proved theorem 2, which is let G be a finite commutative group of order n. If m is a positive integer such that m d by n, then G has a subgroup of order m. For task 2, it asks us to answer the question. The question given is, if m is a positive integer that divide n, does G contain a subgroup of order m? So for the solution, if m is a positive integer that divide n, then it does not always simply show that G contains a subgroup of order m. But if G is a finite quantitative group, then there always exists a subgroup of order m. For example, we take A4. A4 is an alternating group which has the order of 12. So we take m equal to 6, which is the positive integer, then n equal to 12, which is the order of A4. So 6 divide 12, but we know that in A4 there is no subgroup of order 6, so it shows that if m is a positive integer that divide n, G does not necessarily contain a subgroup of order m.
Okay, next I will continue with task 3. Task 3 asks to prove theorem 3. Okay, theorem 3. Let G be a non-trivial group. Then G is a finite P group if and only if order of G equal to P to the power of K for some positive integer K. For the solution, okay, we let G be a finite P group. We must prove that pi G is equal to P to the power of K for some positive integer K greater and equal to 1. Okay, for this, it is sufficient to prove that P is the only that can be divided by pi G. So, by the contradiction, okay, we use contradiction. Let Q be another possible prime that can be divided by pi G. Okay, by the Cauchy theorem, there exists an element of X such that pi X is equal to Q. X, which is X is element of G and G is a P group. So, pi X is equal to P to the power of R for some R greater and equal to 1. So, kita gantikan pi X equal to Q dalam pi X equal to P to the power of R. Jadi kita akan dapat, bila kita gantikan pi x tu equal to q, kita akan dapat q equal to p to the power of r, or p to the power of r is equal to q, where r is element of z. So we get p divided by q, which is contradiction, because p and q is prime. We know that prime can never divide by another prime. So p is the only, so we can prove that p is the only prime that can be divided by pi g. So pi g is equal to p to the power of k, where k is element of z. Okay, conversely, we have given pi g is equal to p to the power of k, where k is element of positive integer and g is a p group. So we let x is element of g be any element. Then we write as pi x divided by pi g. We substitute that pi g is equal to p to the power of k. So we get pi x divided by pk, where p is a prime number. Or we write as, or we substitute as pi x is equal to p to the power of r, for r is element of z, where r is greater and equal by 1, or less and equal by k. Hence, order of every element of G is some power of P. So G is a finite P group if and only if order of G is equal to P to the power of K for some positive integer of K.
Now we are moving on to our task 4, which is the question is to find two examples of P group. So now for example number 1, we start with the theorem that every silo P subgroup is a P group, but not every P group is a silo P subgroup. So first, we let G be a group of order of 520. We'll do some prime factorization, and from there we have 520 equal to 2 power of 3 multiplied by 5 multiplied by 13. So now we are letting NP denote the number of silo P subgroups of G. So from there we can see that N2, or number of silo 2 subgroups, have the possibilities of 1, 5, 13, and 65. And 5, they have possibilities of 1 and 26. And for N13, we have possibilities of 1 or 40. So now, suppose that neither N2 and 5 nor N3 equals to 1. We need to calculate the number of elements for the order. So for now, N13 is equal to 40. And there are 40 multiplied by 13 minus 1 equal to 480 elements of order 13. Now for N5, N5 is equal to 26. By using the fencing formula, we can calculate that 26 multiplied by 5 minus 1 equal to 104 elements of order 5. So now, when we sum up the number of elements for order 5 and order 13, we already have 584 elements in G, which is impossible. Hence, at least one of N2, N5 or N13 equals to 1, and so G is not simple. Okay, so now we are moving on to our second example. We need to let P and Q be two different primes. So now we can show that every group of order P squared Q has non-trivial normal divisor. So now we apply the silo in the same way as in the following example. So we let G be a group of order 105. We do some prime factorization. We have 3 multiplied by 5 multiplied by 7. So now the third silo set, the Sn denotes the number of silo, the silo P groups of G. So S3 congruent to 1 modulo 3. So S3 divides by 35. So now we have 1 or 7 possibilities for number of silo 3 subgroup. As well for S5 congruent to 1 modulo 5. S5 divides by 21. We have possibilities of 1 or 21. So for S7 congruent to 1 modulo 7. S7 divides by 15. And now we have 1 and or 15 possibilities for a number of silo 7 subgroup. From there, we know that P and Q are discrete primes. So silo P has order of P square. So that we can see that SP congruent to 1 modulo P, SP divides by P square Q. And from there we see that there is 1 or Q possibilities for number of silo P subgroup. So now silo Q has order of Q. So SQ congruent to 1 modulo Q. So SQ divides by P square Q. So now there are 1 and P possibilities of number of silo Q subgroup. So now if there are P square subgroup of order Q, each has Q minus 1 distinct elements of order Q generating the subgroup. So thus order P square is equal to P square Q minus P square multiplied by Q minus 1 elements can have order 1, P and P square. So this implies that there can be only one subgroup of order P square on SP with the possibilities of 1 or Q in number of silo P subgroup. So I think that's all. Thank you. Moving on to our next task.
Okay, so in task 5, we were given theorem 4, which is let G be a finite group of order P power of Rm, where P is a prime. And R and M are positive integers, and P and M are relatively prime. Then G has a subgroup of order P power of R for all K, where K is between 0 and R. And we were also given corollary, which is let G be a finite group and P be a prime. If P power of N divides order of G, then G has a subgroup of order P power of N. So in task 5, we were asked to find the definition of a maximal subgroup of the group G. So the definitions that we have found is that let G be a group and let M be a proper subgroup of G. Then M is a maximal subgroup of G if and only if for every subgroup H of G, M is a subgroup of H and H is a subgroup of G, either H equal to M or H equal to G. Or a subgroup M of a group G is maximal if and only if M is not equal to G and there is no subgroup H of G such that M is subgroup of H and H is subgroup of G, which means M and G are the only subgroup that contains M. So the meaning of this definition is a maximal subgroup of a group capital G. Well, first and foremost, it must be a proper subgroup of the group capital G, which we denoted by capital M here, and M is going to be a proper subgroup of the group capital G. The symbol is less than here. That means M is a proper subgroup of G. An additional condition is that in order to be a maximal, it cannot be contained in a larger proper subgroup of G. And the nice way of writing this is that if we have some other subgroup of H that is in between the maximal subgroup M and the entire group capital G, we write here H is greater or equal to M, where M is a subgroup of H and H itself is going to be a subgroup of G. So if we get some subgroup in between the two, it is not properly in between the two. It has to be case that either H is equal to M or H is equal to G, that is not properly in between M and G. It is a fake subgroup that's between them. So it's either M subgroup of H or H subgroup of G that is not actually properly in between maximal M and entire group G. So means here there is no proper subgroup of the group capital G that itself properly contains the subgroup M, if indeed M is a maximal subgroup. So the definitions of maximal subgroup is indeed fits its name because it is maximal with respect to proper subgroups. There is no larger proper subgroup other than it, which by large I mean is properly contains the maximal subgroup M. And a little note here, that is a maximal subgroup of G is not maximal among all subgroup of G, but only among all proper subgroup of G. So maximal subgroups are sometimes called as maximal proper subgroup. And maximal subgroups always exist in non-trivial finite groups because the subgroup form a partially ordered set under inclusions. So since the set subgroup is finite, this partially ordered set will have a maximal element. But note that not all groups have maximal subgroups. For example, the rational number under addition operation have no maximal subgroups.
So now I will proceed with the next question. From the second definition, we let G be a finite group and P be a prime. A subgroup P of G is called a silo P subgroup of G if P is a maximal P subgroup of G. So for the question of the task 6, we need to identify all the silo 2 subgroup of symmetric group S3. So for the solution, we consider the symmetric group of S3 is 1, 1, 2, 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. So we have 6 number of elements. So by the third silo theorem, if G is a finite group and P divide modulus of G, then the number of silo P subgroup of G, which is NP, is NP equal to 1 mod P. From the question, they want the silo 2 subgroup, so our P is 2. So we get N2 equal to 1 mod 2 since our P is 2. So we get N2 equal to 3 because the remainder of the 1 over 2 is same as for the remainder for the N2 over 2, which is 3 over 2. So from the N2 divide modulus of G, which is our N2 is 3, divide modulus of G has order of 3, which is our H is 1, 1, 2, 3, and 1, 3, 2. So when G has an element of order P, thus a subgroup of P is order 2 since our P now is 2. Hence the answer for this task is H1 equal to the bracket of 1 and the bracket of 1, 2 subgroup of S3. Our H2 equal to the bracket of 1 and the bracket of 1, 3 subgroup of S3, and H3 equal to the bracket of 1 and the bracket of 2, 3 subgroup of S3. Now I will pass to the next presenter.
Okay, for the task 7, the question asks to show that every group of order 45 has a normal subgroup of order 9. Okay, this question is related to the theorem 5, which is let G be a finite group of order P to the power of R multiplied by M, where P is a prime, R and M are positive integer, and P and M are relatively prime. Let P be a subgroup of G. If P is the only silo P subgroup of G, then P is a normal subgroup of G. Okay, so the solution. First, we must take the silo theorem. Okay, the silo theorem states that for every primal factor P of the order of finite group of G, there exists a silo P subgroup of G of order P to the power of R, and P to the power of R is the highest power of P dividing modulus G. Okay, if NP is congruent 1 mod P, then we say that the unit silo P subgroup is the normal in G. Okay, let's modulus G is equal to P to the power of R multiplied by M, where GCD of PM is equal to 1. Okay, this is the basic theorem of the silo theorem. Okay, so we write as modulus G as a group of 45 equal to 3 to the power of 2 multiplied by 5. So the GCD of the 3, 5 is equal to 1. There exists a silo 3 subgroup of G of order 9. Okay, we say as a silo 3 subgroup is because the highest power is 2. But the element of P is 3. That's why we says that as a silo 3 subgroup. Okay, the possible divisor of 45 is 1, 3, 5, 9, 15, and 45. Okay, from the possible divisor, we must check the congruence of each element of the possible divisor to get the unit silo 3 subgroup. Okay, so the concept is N3 congruent 1 mod 3, where N3 is the possible divisor, which is 1, 3, 5, 9, 15, and 45. Okay, so we check one by one. 1 is a congruent by 1 mod 3 because when 1 divided by 3, we get remainder 1. and 1 divided by 3, we also get the remainder 1. So we says that 1 is congruent 1 mod 3. Okay, for the 3, for the possible divisor of 3 is not congruent 1 mod 3 because when 3 is divided by 3, we get the remainder 0. But when 1 divided by 3, we get the remainder is 1. So we says that 3 is not congruent 1 mod 3. Okay, same goes for the element of 5, 9, 15 and 45, which is not congruent 1 mod 3. Okay, since only n3 equal to 1, satisfy n3 congruent 1 mod 3, this shows that there is one unique silo 3 subgroup of a group in order 45. Okay, so next we let group P is equal to 9, where 3 to the power of 2 multiplied by 1, we get 9. So the GCD of 3, 1 is equal to 1. There exists a silo 3 subgroup of G of order 9. Okay, just what I said before, silo 3 subgroup is come from the highest power. Highest power is 2, but the element of P is 3. So we says that as a silo 3 subgroup. Okay, the possible divisor of 9 is 1, 3, 9. So we must check each element of possible divisor. Okay, to know the congruent. Okay, the concept is same like I just before, n3 congruent 1 mod 3. Okay, so we must check the each element of n3, 1 congruent 1 mod 3. This is because 1 divided by 3 we get the remainder 1, and 1 divided by 3 we also get the remainder 1. So we say that 1 congruent 1 mod 3. Okay, for the element 3 is not congruent 1 mod 3 because when 3 divided by 3 we get the remainder 0, but 1 divided by 3 we get the remainder 1. So 3 is not congruent 1 mod 3. Okay, same goes for the element of 9. It is also not congruent. Okay, from the corollary, since only n3 is equal to 1, it is satisfied n3 congruent 1 mod 3. This shows that there is one unique silo 3 subgroup of a group in order 9. Okay, a silo P subgroup of finite group G is a normal in G if and only if the only silo P subgroup of G. Okay, hence it is proof every element of order 45 as a normal subgroup of order 9.
And lastly, for the reflections, what we have learned from the assessment is that at the end of doing this assignment, our proof technique had been improved by demonstrating the subject that is not covered, such as different types of theorem and corollary. We also become more familiar with silo P subgroup of a group, and we have learned how to identify it for a particular prime number P. Therefore, by doing that, we can prove its relations with other concept of normal subgroup. So that's all from us. Thank you.